Hello, everyone. So we're gonna, in this video, we're gonna investigate the area between two curves. So we're gonna start with the following situation. I've drawn a little sketch of a couple of functions here. I just called them f and g. And we're gonna start with the assumption that f is greater than g, that both f and g are continuous on the interval from a to b, including the endpoints. And we want to find the area of the region, right, between A and B and between these two curves. So the region we're talking about would look like this, okay? So let's think about how we could find this area. One way to think about it is to go back to thinking about rectangles, right? If I were to approximate this rectangle here, right? I'm just drawing one. Remember the original way we did all of this, we made all these approximating rectangles. The width is going to be delta x. The height is just going to be the difference between these two functions, f of x minus g of x, right? Whatever the y value up here, we subtract the y value down there and we get the height. Notice something, I've drawn it where both are positive, but all I've insisted is that f is greater than g. If g were instead, say, all the way down here, this drawing still works with a little bit of change to it, right? I just have to make this rectangle, let's see, I'll just draw over it. I just have to think of this rectangle as being now much taller, right? And so now this height from there to there is still f minus g, right? Because if f was up at, say, 7 and g was down at -3, the distance between them is 7 minus -3 or 10, right? So it's still going to get the correct height and get the difference between these two, okay? So what this works out to be is when we do our sums, right? Our sums where we would do something like f of x I sub star delta x minus, actually, pardon me, let's put that delta x on the outside. We'll have minus g of x sub I star delta x. And where is this going to lead to in the limit? Well, the area between them, and the area between on A, B is the integral from A to B of f of x minus g of x dx. Okay, so I think this one makes pretty good intuitive sense, right? It's a pretty, I think, clear idea. Let's go back to the original drawing. Get rid of this stuff. We'll move this back up. Looks about right. All right, and so you can see how subtracting these would make sense. Another way to understand this is to use our properties of integrals. All right, again, let's go back to this picture. I'll erase some of the stuff that's in the way. The first integral here, the integral from a to b of f of x dx, would represent, let's see, the area from a to b actually we can just use the blue. All right, underneath f, which is going to be all of this area. And then we are subtracting the area below g. That's what the second integral is, right? And so what we're left with is the area between them. This again still works if g is below the x-axis, because then the area is negative, so you're subtracting and then adding it. You're subtracting a negative, so you're adding that, that area down there and getting this total area between. So let's do an example of this kind of a problem. And what this might be useful for is if you're trying to see the difference between two things, right? So for instance, if I had two, let's say, rockets launched and I knew their velocity functions and they were different, right? If one was faster than the other, its velocity function is always greater. Then the difference between them, well, when we compute the area of a velocity function, we get a distance. When we compute the area between those two velocity functions, we would get the distance between those two objects at a time, right? You'd be taking the total distance traveled by one and subtracting the total distance traveled by the other. So it will tell you how much more distance is gained between them over that interval, right? If you don't know how far apart they were when you started, you don't quite know the total distance between them, but you at least know how much more distance is between them over the interval. Or if two things started at the same time, you would, from the same place, you would know how much further ahead one was than the other. Okay. All right, so let's do an example. Let's say I want to find the area. Let's do black. Oops. Oops, I'm in the wrong, pardon me. I've got two drawing programs open. Let's stick with this one. Let's find the area between f of x is equal to negative x squared plus 7x minus 5. Okay. And g of x equals x. Right? Now, this statement up here is the area between two things on a given interval, but I've given you no interval here. Sometimes the interval is implied by the situation. So let's just take a look at, let's sketch a graph of these two things. Okay, so let's think about what we have. We should know what the graph of g of x looks like. This here is a downward facing parabola. It will have roots at x equals, just using the quadratic formula, negative b. It doesn't look very factorable, so let's go with the quadratic formula. Negative 7 plus or minus b squared minus 4ac is going to be minus 20 all over 2a. Let's approximate this thing. Well, first we can do one more. It's going to be negative 7. Actually, let's do this. Negative 7 over negative 2 will give me a positive 3.5. All I'm trying to do is make a sketch, so I just want to get reasonable locations for the roots. And it'll be plus or minus the square root of 29 over 2. What's this going to be? Well, the square root of 29 is got to be between 5 and 6. A little bit closer to 5 probably, so let's say 5.4 over 2, which is 3.5 plus or minus 2.7. So this gives me roots at x equals approximately 0.8 and 6.2, right? I'm just doing a sketch. You could pop root 29 into a calculator if you want more, but it doesn't seem very necessary. And I can graph this, just a quick sketch. It's always nice to look at what we're doing, and it's always good to be able to quickly sketch these kind of things. So this is a downward facing parabola. It's got a root just below 1. I'll put that right here, and another root up at 6. And we could figure out the vertex if we want, but I don't think we're going to need it. And then the function g of x equals x is going to be some line like this, right? So the area between them, well, it can't be the area out here or over here because those are infinite areas, right? That just keeps going forever. So the implied area between them has got to be this, okay? And so what we need to figure out are the intersection points of these to know the interval in order to use this statement. So let's go ahead and do that. Now I have a graph of this function, nicer than the one I did. I still think it's important to be able to graph on your own. Helps you understand what these things are. And just for curiosity, our roots, oh, we were pretty close, 0.807, 6.193. So that's the picture, right? That's what I just sketched out. Again, we could, I'm not going to use the computer to know those intersection points. You may have just seen it, but we're gonna solve for those. This is also a good skill for us to have. So we need to find out where these two things intersect, and the way we can do that is finding out where their y values are the same, right? Meaning when is the output of this equal to the output of that, and we'll need to subtract x to the other side. I'm going to multiply the whole thing by negative, and then it factors into x minus 3. Nope, not x minus 3, pardon me, x minus 5 and x minus 1, right? Gives me that. So my solutions to this are x equals 5 and x equals 1, right? So if I've done all my work correctly, those are the two intersection points, and what you would want to do is compare. Is f of 1 equal to g of 1? Let's go ahead and do it. It's probably been a little while. So f of 1 is negative 1. We get minus 1 minus 5 plus 7. So that should be 1. And g of 1 is also 1, which is what we got here. F of 5, we want it to be equal to g of 5, which is equal to 5. Let's see what f of 5 is. Negative 25 plus 35 is positive 10, minus 5 is 5. So those are our two intersection points. And so now we know exactly the integral we want to take to compute this area. We're going from x equals 1 to x equals 5 of f of x minus g of x, which is going to be the integral from 1 to 5 of negative x squared plus 7x minus 5 minus x dx. This is the integral from 1 to 5 of negative x squared plus 6x minus 5 dx. Antiderivative, well, our power has to go up. We get 3 in the denominator. Our power has to go up from the x. We want a 2 in the denominator, but we have a 6 here already, so let's just write 3 and minus 5x, and then this is evaluated from 1 to 5. So putting in 5, we get negative 125 over 3 plus 75 minus 25, minus putting in 1, negative 1/3 plus 3 minus 5. Let's just do a little math, a little arithmetic. Let's see, we've got negative 125 thirds plus 25 minus, we'll have negative 1/3 minus 2. Just check for 1 second. Well, let's see what happens. This seems off right now, but maybe I'm just doing too much in my head. So this is what? Negative 125 thirds plus 75 thirds. And then I get minus a negative, so 6 thirds minus negative 7 thirds. Something's definitely off because I'm getting negative 50 thirds plus 7 thirds, but that area is clearly positive. Let's take a quick look to see if we made a mistake. Negative x squared plus 7x minus 5 minus x gives me negative x squared plus 6x minus 5. This is the derivative. 3 comes down squared, 6x -5. That seems strange. What did I do wrong? Oh, 75 minus 25 is not 25. Pardon me, that should be a 50. All right, that's where the error was. Let's redo this. And just to be clear, if I hadn't noticed that right then, kind of going through it all in my head, I was going to start over, because it's not, I find it not that fruitful to spend loads and loads of time looking for an error. It's really hard to see. I feel pretty lucky that I caught that and didn't just have to start over. So this gives me plus 150 thirds, right? So I just subtracted 75 minus 25 and got 25 instead of 50. All right, and then we're going to have minus, what did we say over here? This is minus 6/3, so minus negative 7/3. So now this makes sense. We have 25 thirds plus 7/3 equals 32 thirds. Okay, so a few things. One, that represents the area here. Okay, we could do a quick estimate to see if this is reasonable. 32, what did we get? 32 thirds is a little bigger than 10, right? Let's estimate here. We go from about 1 to 6, so we've got a width of 5. And a height of 7. So if I drew a rectangle around this whole thing, it would be an area of 35, but we're missing a whole bunch of it. It's a really ballpark, but that looks like about a third of the rectangle I can imagine over this shape, right? So it's at least reasonable. The other thing is, notice the error that I made, right? So this is actually a fortuitous, I'll pretend like it was a nice plan to have that error in here. It's pretty fortuitous to see what happened though, because that was a pretty reasonable error. In my head, I did 75 minus 25 got me 50, and then somehow I did 75 minus 50 got me 25, and kind of swapped those two numbers, right? Those are values of quarters, so they all kind of ran around in there. That's a forgivable mistake, right? We're all going to make those computations. I think all of us can do 75 minus 25 and just you know, punted it there. What's important is that I noticed immediately that I was getting a negative number for the area, right? At first I thought I saw that, and I was like, let me just finish the computations and double check. And I did indeed get a negative area. And instead of just going, okay, I thought about the problem, I looked at what I was doing, and I knew I wasn't supposed to get a negative area, right? This will give us a positive area. And so there had to be a mistake somewhere. And this is a really key component. Another thing is, if I had done that little rectangle idea, right? Let me maybe draw that a little bit to be clear what I was doing. In my head, I was imagining a rectangle from about 1 to 6 up to a height of about 7. That's approximately the rectangle that contains this shape. And its area is 35, right? Looking at this, that greenish area is roughly a third, so getting an area of about 10 seems reasonable looking at what I'm seeing here, right? This blue line kind of seems to cut it in half, and then so that would be down to about 17, and then we're getting less than that. So that's not a great estimate, eyeballing it, but it tells me 10 2/3 is in the right ballpark, okay? It doesn't guarantee I'm right. On the other hand, if I did an eyeball estimate, and let's say this height was instead something like 20, and so this big area was supposed to be 100, I would say this green shape has to be bigger than 10, and I would know I had a mistake. Similar to the notion of, you know, you should always try to have something in your head that's a reasonable estimate if you can. Is the answer supposed to be positive? Is the answer supposed to be bigger than 1,000, right? Any kind of reasonable estimate can help you catch those silly errors that throw your answer off by a bunch. Okay, let's do one more problem here. So we started this by assuming when we had the area between two curves, we had f and g where f was bigger than g. On the other hand, or further, let's suppose now that that's not the case. Suppose I have the situation where f and g, let's get a x-axis in here. Let's say I had f and g where maybe they cross. Here's f. Make this one g. Okay. And let's say I still want the area from A to B. Right? The problem is now if I do the area from A to B of f of x minus g of x, over here in this, let's color it in green, over in this area, that's going to work just fine. F is larger than g, so it's going to be positive. In this area, though, as we move over to the right, now g is bigger than f, so f minus g is negative. We're going to get a negative area. And if I don't care about the negative, and sometimes we don't, we just want the area between them, we don't want it to be negative. Okay. How do we fix that? An absolute value. Okay. Now, that's a really easy thing to write. Okay. But what it means we have to do is the following. Let's call this point where they intersect C. I would have to compute A to B, f of, sorry, not A to B, A to C, f of x minus g of x dx. And then, right, because there, that's just like our original work. We have f greater than g, we just take the difference between them, f minus g. Now where g is greater than f, from C to B, that's a C, it looks a bit like an A, let's fix that. Whoops. We have to do g of x minus d of x, minus f of x dx. Okay, that looks terrible. Let's fix that. Pardon me. Okay. So that's what it actually means in practice. And if they were to do something like this, if we had a picture where f went like this and g went like this, we might have to break it up into 3 or 4 or 10 or 50 intervals. Okay, so we have to be a bit careful about that. It's not quite as simple as we want. Okay, now intuitively, or not intuitively, that's the wrong word. I use that word too much. Anyways, when this has an application, when this means something like the example I gave before, if I had 2 rockets being launched into space with different velocity functions, if one was always faster than the other, the area between their 2 curves represents how much more distance the faster one has traveled. However, if sometimes one of them's faster, then the other one catches up and becomes faster, the total area between them will tell us which one, the area between them without the absolute value would tell us which one got further, right? First, in this example, if I didn't take the absolute value, this would tell us how much further f got ahead, but then g starts to get ahead, and we add that area, we'd find out how much now g has passed them by. So whether or not you need the absolute value depends on what the meaning is. Geometrically, if we want the area between them, we're going to take this absolute value. So let's do an example of this. Let's find the area between, what did I want? Sine of x and g of x equals cosine of x on the interval 0 to pi. Okay. So, same idea. Let's start by sketching a graph. Again, as before, in just a moment, I'm going to pull out a nice computer graph. but I really do believe it is good for our intuition to practice sketching these things. It's really hard to make good, educated guesses about problems if you don't have nice pictures of the things you're talking about in your head, right? So that's one of the things that graphing does for us, is it really helps us get some good intuition about the stuff we're dealing with. Okay, so let's mark 0 to pi here. I'll just do it this way. Here is 0. Let's put pi right here. Let's mark off pi over 2. That seems good. All right, let's start with sine of x. I'll make sine of x green. At 0, sine of x is at 0. It increases to 1 by pi over 2, and by pi, it's back to 0. So it's going to look something. The first half was looking so good, and then I got into an awkward position. All right, there's the first graph. Let's do cosine of x. Cosine of x at 0 is at 1. By the time we get to pi over 2, it's at 0. And by the time we get to pi, it's at -1. And it's going to look something. This direction's way harder for me. All right. That's a decent graph. Okay. So looking at this, right, we're going from 0 to pi. The area between them over here, we have the red graph, cosine of x on top, and then the area over here, we end up with sine on top. Okay, so the first thing we need to do is figure out this intersection point. Okay, so let's label this. This is sloppy of me. Let's call this is f of x. This is g of x. Okay, all right, let's find out where they intersect. Start with sine of x equals cosine of x. So how do we solve this? There's a few things we could do. You might just remember, okay? So if you know your unit circle, this might be something that pops into your memory. But let's assume we don't know that and we need a way to solve this. We can do some algebra. And the first piece of algebra I'm going to decide to do is to divide both sides by cosine. Here's the trick though. Every time you divide by something, you're discounting the possibility that it's equal to 0, right? Yeah, I guess that's all I need to say about that, right? We're discounting the possibility that it's equal to 0. Oh, here's an example. If I said x squared equals 2x, if I divided both sides by x, I get x equals 2, which is true. That's a solution, but it's not our whole solution, because when we divided by x, we threw away the idea that x was equal to 0, but actually this equation is also solved by 0. So we lost that solution when we divided. So we have to be careful when we divide by 0. So in this case, I have to make sure before I divide, is 0 a solution? Or is there a time that sine and cosine are both 0 at the same time? And they're not, right? I mean, pretty much by definition, they're not true, because they're defined on the unit circle, and the unit circle, they're defined as the x and y coordinates. One way to define them is the x and y coordinates on the unit circle, and that never passes through the origin. So there's never a time when they're both 0. So we can go ahead and divide by 0, because none of our solutions are going to be when cosine equals 0. So we get this, tangent of x equals 1. And again, this might be one you know, right? There's a few ways to interpret tangent. One of them is the slope of the radius of the, if you have your unit circle, you have your theta here, right? Tangent of theta is the slope of this line, right? And when would you have a slope of 1? When it's, you know, right in the middle. in between 0 and pi over 2. That's one way. You can use tangent inverse on a calculator if you don't remember that. In any case, the only solution we get between 0 and pi is when x equals, let's just write it this way, the inverse tangent of 1, which is pi over 4. Okay, there are other solutions, right? There's one over here if you keep wrapping around the circle, but we're only looking in this interval between 0 and pi. And so I know now that this intersection point is at pi over 4. Okay, where both sine and cosine are equal to root 2 over 2. Okay, so now we've got the setup, right? That's one of the fun parts of these problems is they show up in a calculus class, but so far we've done no calculus on this problem. All I've done is graphing from a trig class and some algebra. So let's get to the calculus part. If I want to do the area between these two functions, let's look at, let's see, from 0 to pi, and we're going to do f of x minus g of x, except I want the positive area. Then this is going to be 0 to pi. Well, from 0 to pi over 4, that's where cosine is bigger. So cosine of x minus sine of x dx, plus pi over 4 to pi, where sine is bigger. So sine of x minus cosine of x dx. So these are the two integrals we have to take. So antiderivative of cosine is sine of x. Antiderivative of negative sine is cosine. So that becomes positive because when you take the derivative of cosine, you'll get that negative sign. And this has to be evaluated from 0 to pi over 4. And then we're going to get, let's see, the derivative or the antiderivative of sine is going to be negative cosine of x. And the antiderivative of cosine is negative sine of x, right? So again, if you're a little confused, take the derivative. It's really hard going back and forth between sine and cosine. It's just going to take some practice. The derivative of cosine is negative sine, but we have a negative here, so it becomes positive. The derivative of sine is cosine. The negative here carries on. And this one is evaluated from pi over 4 to pi. All right, what do we get? We get sine pi over 4 plus cosine pi over 4 minus sine of 0 minus cosine of 0. Oops, I'm running out of space. Let's add some more space here. Oh wait, I forgot this thing scrolls to the side too. Sorry, I'm not running out of space. I have infinite space. Then we get plus, we'll get negative cosine of pi minus sine of pi minus negative cosine of pi over 4 minus sine of pi over 4. Okay, I just decided I don't like scrolling this far right. I want to work down, but we'll finish this one up from now on. Okay, sine of pi over 4, root 2 over 2. Cosine of pi over 4, root 2 over 2. Sine of 0 is 0. That goes away. Cosine of 0 is 1. Then we get plus negative cosine of pi. Cosine of pi is negative 1, so negative 1 gives me a plus 1. Sine of pi is 0, so that goes away. Then I get minus cosine of pi over 4 is root 2 over 2, so I'm going to get, because of the minus sign right here, I'm going to get a minus root 2 over 2 minus root 2 over 2. Okay, we're almost there. Half of root 2 plus half of root 2 gives me root 2. I've got a minus 1 here and a plus 1 here. Then I've got a minus, so these two things are taken care of. The minus 1 and the plus 1 cancel. I've got minus If I distribute this minus, these become plus. This is half of a root 2 and half of a root 2. I get another half of a root, or full root 2, which is 2 root 2. Okay, and there it is, right? So the calculus in here was actually pretty straightforward. I mean, it doesn't have to be. We could have more difficult functions. But I suspect a lot of the challenge here is going to be remembering our trig and our algebra to do some of these computations. So here is that work again, right? It just becomes an exercise in keeping track of all these values. Let's do one last thing since I've got the graph ready. I have a graph of that one we just did, done by a computer. Make it a little bit nicer. So let's close this one. There's that one. Just to see that it's the picture, the nice picture we got, right? There was our sine and cosine graphs. From 0, there's pi at just better than 3. And this intersection at pi over 4 and root 2 over 2. Okay, so there's a nice picture of what that looks like without my scrawl. Okay, that should do it for this one. Thanks, everybody. I will see you next time.